still do that. That's okay. That's okay.
Okay. Have to make sure I don't move. And just start whenever you're ready.
Let's turn the output off so you don't cause an explosion. Yeah, now works.
Cool.
Here we go.
Yeah.
Oh, hey, how's it going? Okay, well, Jake Jarvin here. Nice to see y'all. Right, and I'm looking at you, not that damn thing. That's
tell me where we are.
Well, okay, we got some shit here. Some awesome shit. Awesome shit. Empty, as you can see. Motherfuck. As you can see, this is brand new. I'm just unwinding it now, or opening it now. My birthday present. Well, that's right. 3,140 feet of 20 gauge magnet wire. Enough to make 2 2-foot size Rodin coils, possibly 3. Possibly, if I don't lose my patience and decide to throw out some of the wire because it gets nice and tangled. Right. Just make sure you see that. This big, that much round, and it will look like that when it's empty. And you see. I don't know how well you'll be able to see this, but this is a map for marking out the nodal grid points on a Rodin coil. Very useful, very handy, not hard to make. Protractors, they're beautiful things. Okay, now using that and vortex-based mathematics, you know, whole 3/5, yada yada yada, we wind up with one of these suckers. Rodin coil. This one has 60 winds, this one has 66. We're going to use this to find out the algorithm, difference in frequencies generated by amount of wraps around a specific amount of nodal grids, no points on the grid. Now, there are 4 leads off this coil, 2 positive, 2 negative. We have 1 black here already hooked up, that is, or sorry, we have 1 black here hooked up, this would be the negative. This positive would be hooked up right, one moment, right here. There we go. Now we'd be feeding AC through this using something called function generator, which also recently acquired. It's a DDS signal function generator, runs up to 10 megahertz. This coil here will probably run for around 440 kilohertz, which isn't very much actually. The ones that we'll get will probably run 900, around 900 for a coil twice the size. So yeah. Basically, what's required is when you tune this. Turn this little dial right here. It will actually change the frequency, but I have the output off right now so I don't, fry my nuts here. And so, what we do is we keep turning that up. And eventually, we will hit a resonance with this coil. Resonance implies that we are sending an impulse through this. And at certain junction points, those pulses will overlap, which will actually increase the amount of current running through the coil, but will not decrease the amount of voltage. The way it does this is, see on this side, all the wire seems to wrap around itself. This is because it is forming a cable, because of the way the math goes and the way you wind it. But on the other side here, it still remains all nice and spread out. This will be very, very important. This has to do with the magnetic field oscillation that we're going to be using on the piezoelectric capacitor that's going to be going in the center. Now, as I said, turn this up, reach resonance. Now, like I was saying, I don't know if you can see this from here, but all of you have seen pictures. The way this wire spins, it spins in one direct circle. Well, follows angles, yada yada yada. But as you pulse electricity through this, there will be a magnetic field that is created. Now, piezoelectric capacitor, basically 2 sheets of copper. One's going to be positive, one's going to be negative, with quartz in the center. Now, quartz has a dielectric strength of 1020 volts per centimeter. So for 0.5, sorry, 1020? 1020? No. 1040, sorry, my apologies, 1040. So, for a capacitor that has a dielectric thickness of 0.5 centimeters, which is what we're going to be using, we are going to have a threshold of 520 volts, which means the capacitor that we are building, which is going in the center here, which is going to have pressure oscillate on it from the coil here, will only be able to withstand 520 volts before it will break, which means we want to have it at about 500 volts so that we can induce enough pressure through the Teslas that are going to be created through this coil so that we can achieve the auxiliary charge that we want from the actual quartz itself. Now, as I said with the oscillation, because we have the capacitor in the center, which is going to be charged, both negative and positively, it's actually going to be putting pressure on the quartz, but the oscillation allows for certain points to be more pressurized than other points, which will result in a perpetual charge, because piezoelectricity is both created when pressure is applied as well as removed. So, I'll show you the quartz, just because I know you're going to love that and be nice and interested in it, because I just received it today. It's very thin. I don't know how delicate it is, I really don't. But 520 volts, yeah. See, about that big. And there's 2 of them. Now I'm actually not quite sure yet. I might actually have to overlap these because that would make it a full centimeter. But you see, there's a whole thing. The wider the area of the plates, the more capacitance it has. So that has to do with the whole farad structure and whatnot. Like the amount of farads is the length of a battery life of a capacitor, because a capacitor is essentially just a short-term battery. So we will have less time. We will have, well, less time to hold a charge if I hold it like, or if I build it like this with copper, or with the quartz overlapping itself. This will be a full centimeter. And it will also make, well, it'll last half as long as the other capacitor, but it will be able to attain, well, sorry, reach a higher voltage. So we're going to try it first like this. However, as you've noticed, or as you may have noticed, the hole on this is slightly smaller than the capacitor. Eventually we're going to actually want to make a circular capacitor to put in the very center. This is just for this test. Okay, let's put this back quick. There you are. Okay.
It's a good thing we can edit this stuff out.
Oh yeah. Poopy.
We're keeping that. We're keeping that.
Oh yeah, by the way, Mitchell, because we'll probably have this edited in time that I can show you this. This is your package. It's on its way. Copper powder, graphite powder. Right, so we've got all this set up. Now, as I explained with the capacitor in the center, as I hope everybody understands now, we basically want the capacitor in the center, and as we're feeding it the frequency through the coil, it will oscillate the magnetic field, which will put pressure on the capacitor's plates on specific areas as it rotates, which will cause pressure, which will cause piezoelectricity, which will also continuate or perpetuate the piezoelectricity when the pressure is removed, which will actually create an auxiliary perpetual charge once the capacitor is brought to its dielectric limit, which is around 520 volts. And having it spread out over a large capacitance, i.e. a large area of the plates, we can actually make it last much longer too. I.e. the bigger the coil, the bigger the effect. But anyhow. Now, there was a lot of talk about inverters and all this crap. Inverters are cool. Sorry, not inverters, rectifiers. There's a lot of talk about rectifiers. Rectifiers are cool. They're awesome. But, like, really? You don't need them. Bugger that shit. Bugger that shit. Okay. So, we have our capacitor in the center. Beautiful little thing. Now, there are 4 leads coming off of this coil. All 4 are going to be hooked up to the capacitor. Now, the other 2 leads that come off the capacitor, because it'll have 6 leads, one will be put into an auxiliary battery, which will be charged. That will be our over unity. That will be the surplus of energy. But seeing as we're dealing with a 4-phase conjugate generator, which I'm going to get in the other 2 phases later,